All right, so 2.2 is going to introduce you to a new concept, a concept called the limit. All right, so finally something new. Everything else has been review, right? You've seen it all before. Maybe not quite with the intensity we've been doing it, but you have seen it all before. So we're going to be talking about limits now. Limits are very, very important. They actually form the foundation for calculus. So if you ever go on to take calculus, the limit is the foundation for the ideas in calculus. All right, so think back to what we just did on the quiz. Think back that far. I had you find function values, right? So if I have a function, let's just say f of x equals x squared, and I ask you to find f of 1. You know how to find f of 1, right? What would you do? Plug it in for x, right, and you get 1 squared, which is 1. What does that mean? What does that tell us regarding the graph of f of x? This is your x value. This is your what? Y value. So on the graph, there is an ordered pair 1, 1, right? It's a point on the graph. You can actually go to the point 1, 1 and stand there, right? You could stand on the point. And of course, if you collect enough of those points, back in little algebra 1, you made a little table and you found a bunch of y values based on your independent choice of x, and you plotted those points and you connected the dots, okay? So the function value is a y value. What we're going to learn today is something called the limit value. The limit value. And I want you to know in the very beginning that the limit value is also a y value, just like the function value. It is a y value, but it is the y value, I should say the y value. It's the y value that we, because I'll do it with you, that we approach. That's a key word, rather than actually get to. So the function value is the value that we get to. We go to the point 1, 1. The limit is the y value that we are approaching. And notice, if you look at this graph, you could think of the graph as being like roads. So you kind of have an aerial view. I want to know then, what y value am I approaching? And there's two sides that we could approach it from. As I approach x equals 1 from both sides, what y value is this graph approaching? Well, drive on the road with me. I'm going to approach it from the left first. So I'm going to hop on this graph to the left of x equals 1, and I'm going to start driving towards x equals 1 on this road that is the graph. And as I get closer and closer and closer to x equals 1, what y value am I getting closer and closer to? I'm getting closer and closer to 1, right? Now, how close can we actually get to that point without actually getting there? Infinitely close, right? There is no, again, first number to the left of 1 on the real number line. So if I'm plugging in, like if I'm actually computing it, x squared, if I plug in 0.99999 and squared it, it looks like I'm going to get 0.99999, right? Something just smaller than 1. If I then plug in 0.9999999, even closer to 1 from the left, and square it, I'm going to get a number that's even closer to 1, but still smaller, like 0.9999999. Similarly, if I get on this road and I approach 1 from the right-hand side, as I get closer and closer to 1 from the right-hand side, it appears that I'm also getting closer and closer to what y value? 1, right? So if I plugged into my calculator, because I'm going to let it do the work, 1.00001, and I squared it, I'm going to be getting something that's really close to 1, but a little bit bigger, like 1.0001, so on and so forth. So we can get infinitely close to x equals 1 from both sides. But it would appear that as I do that, my y values are also getting closer and closer to 1. All right, so why would I need to have this new thing that talks about approaching an x coordinate and looking to see what the y values are doing, when I could just say, if you're interested in what you're approaching as you get closer to 1, why not just go to 1 and see what y value you're standing on? Why would I need this new thing called a limit that talks about approaching an x value rather than just going there? What have we just been studying? 3 types of what? Discontinuities, right? And if we have open circles, we can't go to that open circle, can we? Okay? So we have now this way to describe what the y values of the open circle are, okay? And that's called the limit. So here's how we would write this. Okay, I'm breaking form here with the notes. I would write this work that I just did. I would write it as the limit, which we abbreviate LIM. And you can write it in cursive or you can write it in script. I don't really care, but we're going to abbreviate limit LIM. To show that we're approaching 1 rather than actually going to 1, instead of saying f of 1, underneath the limit, we write x arrow. And that arrow means approaching 1. Now, if we're approaching 1 from the left side of 1, we're going to put a little negative ionic charge looking thing there. That means from the left. And then we put the function that becomes the road on which we travel. We put that to the right of limit, right? So the limit and f of x are written on the same line, and they're the same size, but underneath the LIM, we put our input. X is approaching 1 from the left. All right, and then we're going to go ahead and say, as we saw in the graph, 1. So the way we read that is the limit as x approaches 1 from the left of the function f of x is 1, which basically means as we get closer and closer to 1 from the left, the y values are getting closer and closer to 1. Similarly, we write it from the right-hand side as the limit, LIM, as x approaches 1. And to show from the right-hand side, we're going to use a little positive exponent-looking thing. And again, that gets written a little bit smaller underneath the limit. And then right next to the limit, we put the function whose road we're traveling on. And in this case, again, if you approach 1 from the right, we're getting closer and closer to 1. So again, when we say the limit is 1, this is the y value. When we say the limit is 1, this is the y value. And of course, if we say f of 1 equals 1, that's also the y value. But that's the one we're used to. So f of 1, we show our x input in the parentheses. And then f is the function that we're using to evaluate. But for the limit, we put the x value we're approaching underneath the limit, and we put our function up there. So we have these new y values called limit values. And they're not the values we go stand at, but rather they're the values that we are what? Approaching. Okay, so I want you to always remember that the limit is a notion of motion. We are moving towards an x value, and we're figuring out what the y values are approaching. Okay, sweet. Let's look at this graph down here. Example 1. For the function below, I want you to analyze what is happening to the y values as x approaches 3 from both sides. All right? So we're going to do it graphically. So here's the function f of x. Again, you can imagine that this is an aerial view. What would be, what are we approaching, what y value are we approaching as we approach 3 from the left? We're approaching 5. What y value are we approaching as we approach 3 from the right? 5. Okay? No big deal. So it seems kind of silly again to do this because the function value is also 5. So why would we even want to talk about the values we're approaching if we can actually go there? Well, you'll see on the next example, when we have discontinuities, we can't go stand at open circles. So let's go ahead and write this up. Practicing the notation, we'll say the limit LIM as x approaches 3, we'll do the left side first. Now that means we are approaching from the left side. So we're actually moving to the right when we approach from the left side. Of our function f of x is 5. And then the limit LIM as x approaches 3 from the right-hand side of the function f of x is also 5. And then just for kicks and grins, f of 3 is what? It's also 5. What are we looking for when we ask for f of 3 and we have the graph? We're looking for the y value, which is the dot. Good. We're looking for the solid dot. All right, so that's still what we've been doing all along. That's the solid dot. Now remember, if we're looking like right here, we don't have to put solid dots. We just assume that the function is there. We only put solid dots to accentuate a point. All right, so the limits, you could think of these as the roads, right? The roads coming in, the roads going out. But the solid dot is the function value, okay? So you could think of that, here's a nice analogy. You could think of that as a bridge. It's kind of nice, right? So think about like at x equals 3, we have this purple river that runs through here, right? Maybe it's on Prince's property, okay? And if we're trying to cross the river, because we got cliffs on both sides, we have a road coming in. That would be the limit from the left. We have a bridge that's connected to the road that spans the river. And then we have a road coming out. That would be the river from the right. So if you want to complete the analogy, think of the limits as roads and think of the function values as the bridges at that point, okay? That'll be helpful. All right, example 2, same thing. This one's going to be a little bit more exciting because what do you notice about this function at -4? There is a, is this a jump? If you're sketching it from left to right, I'll give you the fact that you do have to jump up here to sketch the solid dot and jump back down. But remember, that's not what we call a jump. Jump is a vocabulary word now, not just a verb, right? That is a hole. That is a hole. Why? Because it's removable. If I make that dot movable, all you have to do is move it down here and plug the hole. So that's a hole, even though it's defined. All right, for a hole, your roads are lining up each and every time. All right, let's put the notation first this time. What would be the limit as x approaches -4 from the left of f? Hop on the graph to the left of -4 and start traveling back towards -4. As you get closer and closer to -4, your y values are getting closer and closer to what y value? 2. There you go. This is where the limit is very useful because now I can talk about the y value of the hole, whereas previously we couldn't. We could just say there's a hole at -4 too. What would be the limit as x approaches -4 from the right-hand side of f? Hop on the graph and start heading back towards -4. You're getting closer to 2, right? So this is really what defines a hole. The hole is going to be there if your two limits from both sides are the same, if your roads are lining up, essentially. Okay? And then what is f of -4? It's 3, right? So if this were actually like some place you were trying to cross in your car, it's like the road builders and the bridge builders were two different companies and they didn't communicate, right? Because you got the road coming in from the left and it's lining up with the road on the other side going out, but the stupid bridge company built the bridge where? Up there, right? So there's no roads going to the bridge and there's no bridge connecting the roads. So we have a bridge and we have two roads, but they're not lining up. And whenever your bridges and roads don't line up, you have a discontinuity. And it depends on how they don't line up, whether it's a hole or a jump or a VA, okay? So this is very powerful now. Before today, all we could say is f of -4 equals 3, and then we could say there is a hole. F has a hole at -4 too. But now we have a way to talk about the y value of the hole independently from both sides, okay? The function values are the roads, those are the limits, and the dot, the function value, is the bridge. We'll stop right there, okay, for today because we have advisory scheduled.